So now we come into our really the modern atomic theory, which has been around since about 1920 or so. And the first person we're looking at here is Erwin Schrödinger, 1926. He proposed a wave model of the atom. And in this model of the atom, electrons have properties similar to light. Electrons are part particle and part wave. And because they have wave properties, they can be, in a sense, in more than one place at the same time. Also at this time, another famous physicist called Werner Heisenberg came up with the uncertainty principle. All we can know is an electron's probable location, not its exact location. And one reason is that in order to see an electron, we have to shine light on it. And when we do, we move it, so therefore it's not there anymore. Now these together are going to help us come up with what we call orbitals. So what we're going to now take a look at in our modern theory, how we have electrons occupying their energy levels. This is based on the Bohr model. Now we're going to take a close look inside these energy levels and say, these energy levels are made up of orbitals. So within these energy levels, we're going to see that we have different numbers of orbitals. The first energy level only consists of one type of orbital, that's going to be designated S. So in this model here, electrons will travel in pairs. So we only need one pair for the first energy level. Now the second energy level, with 8 electrons, we need 4 pairs. We're going to designate that as an S and then as 3 Ps. Now to distinguish between the S on the first level and the second level, we'll put a number in front. So in other words, this first one is called the 1s because it's the S on the first energy level. And this one is called the 2s. Just like these p orbitals would be called 2p. For 18 electrons, we would need 9 pairs. So you can see we can have an S, 3 Ps, and a new type called D. So we'd have the 3s, 3p, and 3d because it's on the third energy level. And the fourth energy level would need 16 orbitals, an S, 3 Ps, 5 Ds, and 7 Fs. So in each of these orbitals, when there is a pair of electrons present, the electrons will spin in opposite directions, and this helps to stabilize the orbitals. Now the electrons in those orbitals will have different amounts of energy, and the orbital shapes will be different. I do want to point out that it doesn't mean the electrons are traveling funny. No one really knows how they're traveling. Now here is 3 s orbitals, the 1s, which is the smallest because it's closest to the nucleus, the 2s, which is larger in area, further away from the nucleus, and 3s, which is larger still. But these are not, these are not like solids. They just simply represent the probable location for finding an electron. You can find it anywhere within this orbital. This shows us that same idea again, the 1s, the 2s, and the 3s. And the nodes represent the interaction between two waves, and the waves kind of cancel each other out there. Now let's take a look at the p orbitals. I think this diagram over here gives you a better idea of what we're talking about. If you were to plot the probable location of electrons in the p orbitals, let's say at every minute, you wind up with a plot like this with a whole bunch of dots. Now if you fill those dots in and make a solid out of them, they would kind of look like this. Now we can have 3 different p orbitals, one occupying the x-axis, one occupying the y-axis, and one occupying the z-axis, kind of like length, width, and depth. And here we see the d orbitals. 4 of them are kind of cloverleaf shaped, and the last one is an undetermined name. But again, you see how we have these plots, they call these scatter plots. And here are the 7 f orbitals, and I think we have any name for those. Now how do you distinguish between these different orbitals? We see we have little formulas to go with them, but you don't have to know that. What you have to know is that there are 7 f orbitals. Electrons in the f orbitals possess more energy than if they were in a d orbital or a p orbital or an s orbital. Okay, now we're getting to electron configurations, and you probably remember how to write these. So this will describe the most probable location for finding an electron in the ground state. So here's an example, 1s1. So the number 1 means the principal quantum number or the energy level number. Next we have the orbital shape, which we designated with letter S. And then thirdly we have the number of electrons in the orbital or subshell. So this represents then a hydrogen atom. Now we can also show that electron in the orbital by using what we call an orbital diagram. And in the orbital diagram, we use an arrow to represent the electron. So here we have the electron all by itself. Now, if there was a second electron in there, we'd have that arrow pointing down, indicating the opposite spins. So this is what the orbitals would look like if you're talking about a hydrogen atom. You notice that when you are on the second energy level, you're further away from the first. This is going the energy here. Third is further away from the second, etc. But you notice that at the second level, the s and the p orbitals are at the same energy. And the same thing here, 3s, 3p, all the same energy. Now this is really only for the hydrogen atom. The minute you put more than one electron in an atom, you have attractions and repulsions, and these things get a bit skewed. N is 1, N is 2, N is 3, N is 4. So this is a much better diagram to use. This is for a multi-electron atom. You notice now 1s is the lowest energy orbital, then it's 2s, then it's 2p. But you notice the 2p, higher energy than the 2s. 3s, higher than the 2p, lower than the 3p. Now here's something interesting. The 4s is a lower energy orbital than the 3d. That means electrons will occupy the 4s orbital before they'd occupy the 3d. Now there is a way to come up with the order that these things go in. I'm going to show you that later. We're going to use the periodic table for that. Here's 2, okay, etc. All right. So now we're going to use the off-bow principle, which means electrons will occupy the lowest energy orbitals first. We're going to kind of build up and show you how the electrons will occupy these orbitals. You just follow along with this, and I'll go through it slowly. Right. So the first one we're going to take a look at is the hydrogen atom with its one electron. So that one electron would occupy the first energy orbital, or the 1s, in its electron configuration 1s1. Now the next element would be helium with 2 electrons, and its configuration would be 1s2. Now you notice that that second electron is pointing in opposite directions from the first, indicating it has an opposite spin. So therefore all elements past helium will all start the same way with 1s2. So if we do lithium with 3 electrons, it'll have the 1s2 and also then 2s1. And that means that beryllium with 4 electrons would be 1s2 and 2s2. After beryllium comes boron with 5 electrons. We're going to have the 5th electron right here in the 2p. So we have 1s2, 2s2, 2p1. Notice that these first orbitals are filled before we get to the next one. Carbon with 6 electrons. Remember, where would the 6th electron go? Would it go here to pair that up? Or would it go here, all by itself? Well, most of you are probably picking it'll pair it up. But guess what? No. We're going to apply Hund's rule to this, which really states electrons will occupy their own orbitals first before pairing up. This gives them a more stable arrangement. So for carbon, the 6th electron would be here. So the carbon atom has 2 unpaired electrons. Now we can't tell that by the configuration. It ends with 2p2, but you would have to know that these two are unpaired. Nitrogen with 7 electrons has 3 unpaired. And sometimes you're going to be asked how many unpaired electrons are there in the ground state for a particular element. Okay, we can continue on. Oxygen with 8, look like that. Fluorine with 9 would look like this. And then neon with 10 would look like that. So you notice with neon, all of the orbitals are filled. Not only that, the first energy level is filled, and the second energy level is filled. And this is why neon is so stable and chemically unreactive. So here are all the electron configurations written down from hydrogen down to neon that we just went through. Well, sodium would be 1s2, 2s2, 2p6, 3s1, just one there. And once we start to get larger and larger atoms, it becomes kind of cumbersome to be writing all of this stuff down. So I'm going to show you the shorthand method for doing this. In the shorthand method, we use the closest noble gas in size to the element that we want to do the configuration of. So you notice sodium, we're going to use neon. We put the neon in brackets. This is going to represent that whole first layer of electrons. And then we just add on 3s1 to that. So we're going to use neon for all the elements in the row that sodium is a member of. So replace the inner electrons with the closest noble gas. So for magnesium, which is right next to sodium, 3s2, we have neon there as well. But for potassium, which is the first member of the fourth level, we would use argon. So argon has 18 electrons, and looks at that. I think this should be 3s. This should be 3s2. Okay. All right. No mistake there. So write the electron configurations of the following. So you can go back and use the diagram that we had earlier to do this, or there are diagrams in your book that you can use. So for phosphorus, it would be Na3s2, 3p3. Calcium with 20 electrons, argon 4s2, and sulfur with 16 electrons, Ne3s2, and then 3p4. How many unpaired electrons does each element have? Well, 3, none. Some people might think 2. Remember, there's only one s orbital, and 2 for the sulfur. And here we have them here. So notice for the sulfur, 4 electrons. Some people think, oh, that's 2 pairs, but it isn't, because you have 3 p orbitals. Each one can hold 2 electrons. Properties resulting from unpaired electrons. The first one is called diamagnetism. If an element has all of its electrons paired, then that element actually would be repulsed by a magnetic field and would be able to be held by one. When we think about metals being held by magnetic fields, but mostly it's iron. Paramagnetism, unpaired electrons cause an attraction. So paramagnetic elements are those that can be held by a magnetic field, and they all have unpaired electrons in the last orbital. And if you have a lot of unpaired electrons, we have what's called ferromagnetism, strong attraction by a magnetic field. All right, now let's check out one like this, like chromium. Now, if we did electron configuration of chromium, this is what we'd come up with, and that would give us our 24 electrons. We check out the ending of it now, 4s2, 3d4. Chromium shows that sometimes it has a charge of +1, and when these elements become ions, they lose electrons. Now, the outermost electrons, according so far, will be 2. Those are the 4s electrons. So here will be our electrons here that we'll be starting with. Here's the 3d, and we'll see the 3d4. All right. Now, how can we get one of those electrons to leave the 4s and go to the 3d? Notice when this happened, it half-filled the d orbitals up. This would account for the fact that chromium can show us a charge of +1, because it can lose just that one electron in that 4s orbital. So, one thing you want to note, half-filled orbitals are very stable. Now, half-filled, I'm really talking about half-filled d and f orbitals, rather than just half-filled s and p. So, half-filled d orbitals are very stable. That's what we're going to really focus on. So that's the better configuration then for chromium. So you want to note that's one of the exceptions. So we're not going to have any of the elements ending with D4. It won't end with S2D4, it'll be S1D5. Now here's another element we can check out. How about copper? If you look up copper on the periodic table, copper is right next to zinc. So copper has 29 electrons. And that would be its configuration, you would think. The first 18 electrons can be represented by argon, and that'll be 18 electrons. And then we just need 11 more. We get a 4s2, 3d9. So copper, though, shows a positive uncharge sometimes, just like we saw with chromium. So what's going to have to happen is we're going to have to convert it back to 4s1, 3d10. Should have brackets around that AR as well. Okay, so that was our second exception. So elements are not going to end with S2, D9 either. They're going to be S1, D10. So this is a good way to look at the periodic table. Notice that if we go from left to right across the table, we're filling out the 1s orbital, then it's the 2s, and then it's the 2p, 3s, and then 3p, 4s, and then 3d. So what happens now? The periodic table becomes like a map. So just by locating an element on the periodic table, we should be able to write its configuration. That's the way that I do it. I don't bother with any rules. Another way to view it is like this. This will give you the order, 1s, S1 and S2. Here are the P6s, D10, F14. So here's our modern periodic table. So hydrogen 1s1, we go across to helium 1s2, lithium 2s, we'll end with 2s1, then we have 2s2, go across 2p1, all the way to 2p6 for neon. So what you want to notice here is that we're ending with S1 for the alkaline metals. They're all going to end with S1. The alkaline earth metals all end with S2. And here is our P block. Kind of forget about helium up there. This entire block will end with P1, just like this entire block will end with P6. So this is P2, P3, P4, P5, and P6. Now the number that's out in front is simply the number of the energy level. So this is the second, first, the second, the third, the fourth, the fifth, etc. So this would be 3s1, 3s2, 3p1, 3p6. 4s1, that's where potassium was in the fourth energy level, S1. Now 3d1, all the way to 3d10 where zinc is. 4p3, 5s1, 4d1. I just threw some random ones in here so you can see the pattern though. See how they're all ending with D1, D10. So there is a pattern to all this. Here's a P5, 6s1, 5d1. Look what happens after 5d1. We go to 4f1 down here. So that's why you kind of jump down here now. So this would be 4f1 all the way across to 4f14. So after 4f14, where would you go? Right back up here, 5d2, and then continue across the table. Then there's 6p1, 6p6, etc. 6d1, 5f1, 5f14. Okay, so now we're going to write some. And let's just do the shorthand configurations only because the others are just too long. So, what are the shorthand electron configurations for nitrogen, sodium, and vanadium? We just have to locate them on the periodic table. So here's nitrogen. So the shorthand is going to have helium in brackets. They'll just represent the first two electrons. And then we have to show these here. So for nitrogen, it's 2s2, 2p3, helium, 2s2, and 2p3. Now for sodium, which is over here, sodium is going to be, okay, it's going to have Ne in brackets, and then 3s1. And what about vanadium here? That is 23. So for vanadium, we're going to have argon in brackets. So argon represents the first 18 electrons, and this will be 4s1, 4s2, and then 3d1, 2, 3. And that's it. So see, you can use the periodic table to come up with electron configurations for many of the elements. Okay, and that's the end of the show.